Okay, so welcome to the compiler session. And in this session, we have two talks. And the first talk is a keynote talk by Qirun Zhang from Georgia Tech. And he has been making significant and interesting contributions on static analysis. But today, he's going to talk about compiler testing and validation. So please welcome him.
Thank you for the nice introduction. Hi, good morning, everyone. It's of my great pleasure to give a talk at the SAS. And today, the title of my talk is From Within Compiler Testing and Validation via Compilers. Let's get started. So the topic of today's talk is related to compilers. So first question first, what is a compiler? So sounds like a philosophical question. So compiler is actually a computer program. Like any computer programs, it takes some text as input and performs certain computations and then produce the text output. But on the other hand, compiler is also a specialized type of software where in this case, your input is yet another program. And then the compiler will perform certain optimizations on your input program and produce an improved version of your input program. And we want our compilers to be correct. And as a result, and in the past few decades, our research community has developed a lot of techniques to improve the correctness and the reliability of compilers. For example, compiler verification techniques focus on checking the internal behavior of compilers and prove that you have a correct implementation of your compilers. On the other hand, compiler testing and validation focuses on reasoning about the external behavior of your compilers. And some typical examples are translation validation and compiler testing. So in today's talk, we'll be focusing on compiler testing and validation. And let's first consider how do we validate a normal computer program. Suppose that you have implemented a calculator, which is very nice, and the question is, how do you convince your friends that you have correctly implemented a calculator? In this case, most likely that you will also provide a set of inputs, right, to validate the functionality of your implemented calculator. For example, if your input is 1 plus 2, and then you observe the output of your implementation, which gives you 3. That is nice, and it means that most likely that you have implemented a correct calculator. On the other hand, if you give the input as 2 plus 1, and your software produce, well, you're a nice person, right? So this is the typical response that people would like to receive, but it's not anything we would expect from a calculator. Okay, so now let's pay our attention to compilers as well. So how do we validate and test a compiler? Recall that in compilers, the input is not a normal piece of text, but a computer program. Without loss of generality, we assume that this time the input program is a calculator, and the output program is an improved version of your calculator. So now we have yet another philosophical question to answer. So how do you know that your calculator prime obtained from your compiler is an improved version of a calculator? In the previous discussions, we know that validating a calculator doesn't seem to be hard. All you need to do is to give some inputs like 1 plus 2, and if you see the result of 3, that means most likely that you have a correct implementation of a calculator. Now let's put things into perspective, okay? So when we test, our goal is to test and validate the implementation of compiler. In order to perform the validation, we need to provide input to the compiler. In this case, your input is a calculator. And in order to validate the behavior of your calculator and calculator prime, you need to provide inputs to both calculator and calculator prime, right? Only after you can successfully validate the equivalence of the two calculators can you successfully validate the functionality of your compiler. So in this talk, hopefully I can convince you that there's an improved way to do the compiler testing and validation. In this case, we do not need input to validate the equivalence and correctness of the input programs. We just need a piece of input program, and then we can directly utilize the output from your compiler to perform the compiler validation. Okay. So now without the input to program P and P prime, let's revisit what we sign up for. The problem definition becomes that given one input program P and your compiler, you obtain another program P prime. And given these two programs P and P prime, we want to check whether or not P and P prime holds certain properties, where you can define the property to be, suppose as we see in a previous example, you implement a calculator, then this property should have something to do with the property of a calculator. It can also be like terminating properties, like if P terminates, P prime should be terminating as well. It could also be like point aliasing property, like two pointers points to the same location in P, and in your optimized code, you should expect the same thing. Finally, some I/O equivalence properties. For example, if you give 1 to P, you obtain 2, then you should obtain 2 for your P prime as well. Okay. Now let's take a look at this problem definition. It is very similar to a well-known theorem in static analysis, which is called Rice theorem, right? Because all the properties that we discussed at this point are non-trivial program properties. And we know that this problem is hard, right? Like this problem is undecidable. And in static analysis, we have to build over approximations to tackle this undecidability. Okay? So I would like to pause for 1 second and invite us to revisit our problem statement. Okay? Rice theorem is undecidable because we are given 2 arbitrary programs, P and P prime. In this case, is it true that we have 2 arbitrary programs? Okay. In the context of this compiler-like workflow, it turns out that we don't have 2 arbitrary programs. In particular, this P prime is obtained by your compiler. Nowadays, you can safely treat compiler as a white box because most compiler implementations are open sourced. In other words, you can treat your compiler as a deterministic algorithm. And this deterministic algorithm will take as input a program and produce another program P. And our task is to kind of validate certain properties between P and this P prime obtained by yet another like deterministic computer program. Okay, so hopefully you can see that by kind of understanding the connection between P and P prime, we can simplify the problem, and maybe the problem will no longer be undecidable. Okay, so our idea in this direction is that instead of looking at the external inputs to validate the equivalence or property in P and P prime, we choose to look at internals of the compiler. Because according to the previous discussion, this program P prime was obtained by this algorithm, right? And this algorithm is like a deterministic algorithm. And in the ideal case, we could ask this program to produce a kind of traces, right? A set of modifications that the compiler does in order to produce this optimized code. Okay, that's the high-level insight. And to sum up, what we plan to achieve is that we want to improve the reliability of compilers by utilizing internal compiler knowledge. Okay, so in the next 30 minutes, I will be focusing on discussing 2 applications. One application is based on debug information validation, and then the second application is based on validating a loop like a vectorizer. Okay, now let's first take a look at the first application on validating debug information. This is a joint work with my collaborators from East China Normal University, and this paper was published at this year's PODI. Okay, so now we are going to talk about debugging, right? So optimizing compilers will typically generate debugging information to facilitate source code debugging. All you need to do is to give a flag called -g, and now these open source optimizing compilers such as LLVM and GCC will emit debugging information in your binary. And in this case, the input to your compiler is a source program, and the output is kind of a binary. Right? You want to do the debugging on the binary code. And here's an example. And the debugging information essentially establishes the correspondence between your source code program and your binary. and you can launch your binary in your debugger, and then to look at your source code and print certain values and do the debugging. Okay. So to sum up, there are two essential tasks in the debugging process. The first task is the ability to stop at a line, meaning that you should be able to set a breakpoint at, in this case, line 7, and stop at the line 7 in your debugger. And then the second task is about checking the value of a variable, right? So you should also be able to print a value of A and obtain a value to see whether or not it is correct. So in this talk, we will be focusing on the first type of information, which is the debug location information. Basically, we are going to kind of talk about the problems related to debug location, right? So debug location information essentially gives hints to the debuggers that, okay, we can set a breakpoint in your code and then to do the debugging tasks, okay? Now let's take a look at the program properties associated with debugging information. So in this case, we have two programs. P is the unoptimized binary, and P prime is the optimized binary. And you want to perform source code debugging on both binaries, where both binaries are generated from the same piece of like a source code program. Okay, that's the basic setting. And as we discussed, we are interested in validating the program property with respect to debugging information, meaning that the compiler has already generated the debugging information in P and P prime. Okay? Now let's take a look at the scenario. Suppose you can stop at line 7 in your unoptimized program. Okay? Here's the question. Does it imply that you can always stop at line 7 in the corresponding optimized program? So the answer will be yes and maybe yes, right? So sometimes you can, sometimes you cannot, because if the optimizer optimizes certain instructions and those type of instructions happen to be at line 7, then in the debugger, you will typically see that the debugger will tell you that this line has been optimized out, meaning that you can no longer stop at line 7. Okay, I hope that makes sense. And now let's take a look at the flip side of the property. Suppose that you cannot stop at line 5 in your original program. Does this imply that you can not stop at line 5 in the optimized code? No? Why? Yes, the compiler will insert instructions, but okay, according to some input, if you cannot stop at line 5, that means that line 5 is mostly to be dead code with respect to the input, right? And in your optimized code, the optimizer should not revive any dead instructions in your optimized code, meaning that given the same input to P, if line 5 cannot be reached in unoptimized code, line 5 should definitely not be reached in the optimized code. This situation is slightly different from the first case, right? When you stop at the original like P, it might or might not be the case where you can stop at the same line. But if you cannot stop at a certain line, in this case line 5, you can definitely not be able to stop at line 5 in your optimized code. Okay? So just by combining this, we can see that it is like the debugger location property with respect to your optimized code is a subset of the debug location property of your unoptimized code. In other words, your P prime is a refinement of P. Therefore, the behavior of the P prime is a subset of P, which I think intuitively, I think it makes sense. So therefore, to sum up, the information that we want to validate in the context of debugger location validation is that we want to make sure that the debugger location information associated with P is a subset of the property associated with the unoptimized program. Okay? So that's the kind of the oracle. So how do we check this property in the existing approaches? Usually we can validate this property via testing. In this case, the approach is pretty straightforward. You have two programs, unoptimized program P and optimized program, the corresponding optimized counterpart P prime. And you can generate a random input and run your binary in a debugger. And then you can set breakpoints in different locations in program P, and then observe whether or not you can stop at a certain line in your debugger. And therefore, you can collect a set of debugger locations for the unoptimized program P with respect to your input. Okay? And then you do the same thing for the optimized binary P prime, and you can collect a set of reachable locations in P prime. Because we have mentioned that the property we want to validate is that one set is a subset of the other set, and we just once you have two sets, it's very straightforward to check the subset relation. And if this relation doesn't hold, it means that you have found a bug. Okay, so this is basically the general idea behind NA testing work, and we have a paper published at POD 2020 where we kind of use this idea to generate interesting programs for finding bugs in debuggers. And I think we have successfully found roughly 100-ish LLVM and GCC bugs related to debugging information generation. Okay, but in this talk, I would like to convince you that we can do better than testing. Okay, specifically, we notice that in this testing setup, and we always need an input to the corresponding program in order to do the validation. Okay, so in our new work, and we would like to validate the property without obtaining the input to these two programs, P and P prime. How could that be possible? Okay. Now let's take a look at, again, this compiler workflow. And in this case, you have two programs, and P prime. If we take a deep look at the compilers, in the context of debugging information generation, we can see that essentially the compiler will perform two tasks. The first task is what we call instruction manipulation, meaning that we can treat the compiler as an optimizer. The optimizer will kind of change the instruction and add instruction and move instruction and do certain kind of rewriting to improve the efficiency of your program. Okay? And at the same time, because now we are interested in debug locations, right? So whatever you do for certain instructions, you also need to update the corresponding debug location internally, right, within your internal data structures. Okay, that's the only way to maintain the consistency between P and P prime in the context of debugging information generation. Okay, let's take a look at an example. So in this simple example, we have a basic block, and in this case, in the original unoptimized code, we have instruction at line 7, and for some reasons, and the optimizer has decided that we can replace this multiplication with addition. Therefore, we have a new addition instruction at line 7 as well. Okay, so we can actually instrument the compiler and to tell us the instruction manipulations. With the help of this instruction manipulation, we are able to find that the source instruction in the unoptimized code is this multiplication instruction, and the destination instruction S prime in the optimized counterpart is this addition instruction. Right? Again, because compiler is a deterministic algorithm, right? If we instrument those critical APIs, we should be able to derive these facts. Okay? In other words, we can find the correspondence between S, instruction S in P, and then the corresponding S prime in P prime. Okay, that's the first piece of information. Second piece of information is we also, right, in this case, we introduce a new instruction to your program, right? We need to update the debugger information as well. In this case, this new instruction should preserve the the original debugger information of your old instruction. Okay, so this option is called preserve, and according to the LLVM's documentation, we have 3 types of update operations: preserve, drop, and merge. Okay. So if we can instrument the compiler internals, we should be also able to tell what compiler does in order to update your debugger information. Okay. To sum up, we can instrument the internal structure of your compilers and obtain 2 types of information. The first type of information is about instruction manipulations, where we can focus on creation, clone, move, and replacement. Okay. And in terms of debugger location updates, according to the LLVM's documentation, we can identify 3 operations: preserve, merge, and drop. And we can also instrument the corresponding LLVM APIs in LLVM's source code. Okay. Once we have this instrumentation ready, and once we gave an input program P, we should be able to collect a trace of actions taken by the compiler in order to optimize your code and update the debugger location information. So this is basically what we did in our work and to instrument the LVN APIs. And here we kind of listed the APIs that we will instrument. Okay. So to sum up the discussion so far, and we have briefly discussed that it is possible to instrument your compiler and obtain two types of information. The first type of information corresponds to instruction manipulation. The second type of instruction corresponds to debug information updates. Okay. Our next step is basically to tell us that the correctness, right? How do we know that a certain debug information update is correct? That is critical in our validation workflow. Okay, how will we be able to tell that? So in this case, we are going to perform static analysis on P and P prime. Okay, specifically, we will identify some source instructions, and then we will do simple control flow analysis to collect the set of passes that will cover this instruction. And then we can also collect the debug location information in each passes. Therefore, with respect to an instruction, source instruction, we can collect a set of debug locations. And because we have instrumented compiler, right, we can know the instruction manipulations. We can find the corresponding destination instruction with respect to the source instruction. And then we do the static analysis in the optimized binary, find a set of passes that can contain this instruction, and collect the debug location information with respect to those passes. Okay? And once we have these two sets, and we can basically decide the anticipated debug update operation. For example, if the destination set is larger than the source side, recall that we have discussed that the property is that the optimized program's debug information set should be smaller than the original program's debug information set, right? In this case, if that doesn't hold, that means that the compiler should drop the debug location in order to maintain the consistency. And there are other two types of update operations, like preserve and merge. We can obtain this rule by just looking at LVN's source code documentation, and there they describe this updating principles in natural language. We can distill a set of rules, and with the help of these two data structures, and we be able we will be able to infer the anticipated updates, debug information updates. Okay, and again, this source and destination can also be a set, right? We can iterate over all instructions in your source code program. Okay, so let me put together everything. Okay, our goal is to do compiler validation with respect to debug location information generation, and our goal is to get rid of the inputs to P and P prime. What we do is that we gather information from within a compiler. In this case, we collect two types of information. One is instruction manipulation. The other is what the compiler did in order to optimize your compiler, in order to generate the debugging information for your optimized binary. And with the first type of information, we can find the correspondence between an instruction, source instruction, and a target instruction in your optimized code. And with these two sets, source instruction set and destination instruction set, we are able to obtain a debugger location set. And according to these rules, and we can compute the expected debug information updates with respect to your program P. Okay, so in this case, in the orange box, we get what the compiler does in order to update your compiler, debugger location information, and then we also obtain the expected updating behavior according to our static analysis. We just compare these two results, and if we find any inconsistency, then we report the bug. Okay, that is the general idea behind our framework. Okay, now let's briefly talk about the evaluation result. And before that, I'd like to highlight the difference between our new approach and the traditional approach based on testing. In the traditional approach, recall that we need inputs to validate the software, right? Like the unoptimized code and optimized code. And the goal of testing is just to find bugs. And if we can find bugs and we are successful, and we stop from there. But with this compiler instrumentation infrastructure, we can do more than finding bugs. Because if you look at it, right, so we know the behavior of your compilers by instrumenting the debugger location updates. We also know the expected behavior according to like the two debugger location sets. If there's a mismatch, recall what else do we have? We also have a trace, right? We have a trace of compiler actions that leads to these incorrect updates. Now we can take a look at the trace and manually analyze those API calls and find the problem-inducing API calls and try to correct the error. That's the basic idea. So in other words, we can go beyond testing. Okay. So this table summarizes our results, and in roughly 6 months' time, and we have successfully found 46 LLVM bugs related to debug information updates. And most importantly, I think that's the most attractive aspect of our work, is that we can not only find 46-ish bugs, but we can also propose 46-ish patches. And all of the patches are accepted by LLVM developers. And I think, to my knowledge, this is the first piece of work that can propose actual working patches for a real-world compiler system like LLVM. Okay? And on the other hand, because we have analyzed enough data, right? Because we have test inputs and we can analyze the compiler behavior, we are also able to identify issues in LLVM's source code. LLVM's documentation on debugger location information updates. And we actually identified 2 issues: one incorrect description and one imprecise description. And we also report this issue to the developers. And nowadays, the LLVM's documentation has been updated with respect to our findings. Okay, so that will summarize the first discussion on debugging information validation. And before we switch gears and to talk about the second application, are there any quick questions? We can also do the Q&A after the entire talk. Yes?
When you were talking about checking the subset properties, I thought that the lines are different, that the instruction sets are different. Why are they the same? Why can you compare them?
We check the locations.
Locations?
Yeah, like line 5, line 3, line 6, something like that.
Yeah, but this one's programming can contain less lines.
Yeah, so it's a subset relation, right? Not always, but I would say 90% of the chance it will have fewer lines, because the compiler will needs to optimize your program, right, and shrink the code size.
And what if the program is multipliable?
It doesn't matter, right? It will be linked and produce a final binary output. Yeah. Okay. Unfortunately not, but I can show you offline. Yes. Yeah, we have 2 case studies. Yeah. Okay. So now let's, I think I still have 10 minutes, right? 20. Okay, okay. Okay, yeah. Okay, now let's take a look at the second application. So this is an application with respect to like validating a loop vectorizer. This is a joint work with my student Ben. I think he's also here, and also Tom Reps. So this is a work in progress. So we will have a few experimental results to discuss. Okay. So let's talk about loop vectorization. So in this case, the input to your compiler is a loop program, and then the output of your of the compiler is yet another looped program. And in this case, the compiler will identify the optimization opportunities and try to generate vector instructions. One vector instruction can do several things with respect to your scalar implementation. So in this particular example, we can find a vector instruction that can do 8 things at a time. In this case, your original loops like iteration number can be reduced, right? Because now you have more powerful instruction can do 8 things at a time. And so the loop can be split into 2 loops, because if the loop iteration cannot be divided by 8, and you should also have a cleanup loop. That's the basic idea. And you have an input. You have input program counter. So basically, this program poses some challenges for traditional translation validation techniques, because you have to unroll the loop, and the loop bound is actually determined by an input. Okay, so in order to do the translation validation, we will be interested in this I/O equivalence property, because we wanted these 2 programs to be equivalent. Okay, so we will be looking at the control flow graph of the 2 programs. Although in this case, technically speaking, this is not a control flow graph. In this graph, each node represents a program point, and each edge denotes a state transition, which corresponds to basic blocks in your program. Like in this case, we can see that because your original program contains 1 loop, so therefore we can see 1 loop in this kind of control flow graph. And in the optimized code, because this loop will be split into a vectorized loop and a cleanup loop, so we can see 2 loops here. Okay, and we want to make sure that the 2 programs are equivalent, and if they are straight line programs, we can use translation validation to check the equivalence of the 2 programs. But in this case, we have to loop the programs, and the loop structure looks arguably different, right? Okay, how can we do the translation validation? Actually, the idea is based on building a data structure called a program alignment automaton. In this case, basically, we want to compute a product control flow graph based on the original code and optimized code, where in its product, alignment automaton, and each node represents a pairing of the original location in the unoptimized code and the program location in the optimized code. And each edge denotes a set of transitions from your unoptimized code and optimized code. Okay, so with this data structure, we can add assertions. Like, suppose we know that variable j is also a loop variable that corresponds to variable I in your input program. We can add assertions to each program state, and to assert that 2 programs' states are the same. And eventually, we can use a SMT solver to prove the equivalence. So with the help of program alignment, we no longer need to worry about the kind of loop iterations, because in this case, we can successfully align 2 control flow graphs. All we need to do is to validate those state transitions, and to validate the program state are the same before the transition and after the transition. That's why this data structure is very useful in the context of validating a loop vectorizer. Okay, so in a traditional approach, I think we should think about how do we build such a alignment data structure. We do it by testing. Okay, so for your input program, unoptimized program P, we generate some random inputs, and then we basically collect the property. So for example, at program point 2, like in this case, program point 2, this variable I will get 9 values, 0 to 8. Okay, and we do the same thing for the optimized program. In this case, let's say for program 8, and this corresponding variable j gets the value 0 and 8. And we can see that the initial value and the final value are the same with respect to I and j, and they are of the same. They are from 2 different locations in unoptimized code and optimized code. Therefore, we can align these 2 program locations, 2 and B, in the optimized code, and we can add an assertion to assert that the program states should be the same, right? The value of j should be the same, and we keep doing this kind of reasoning for other program points, and until we build the alignment automaton. Okay, and so this is the basic idea behind this PODI work, basically using the program alignment automaton to check the equivalence. So in our new framework, and basically we want to get rid of the need to generate input to validate P and P prime. Instead, we want to get some additional information from the compilers. What kind of information will be useful in this application? Okay, so actually there are 2 types of information. one type of information is about the node mapping. In this case, the location mapping, right? So how could we know that location A should be aligned with location 1 in your original program? How can we get those information? So basically, remember that those are two binary programs, unoptimized binary and optimized binary. We also have the source code, right? In the source code, we also have debugging information, where debugging information will tell you exactly that, like, what is the corresponding source code location of a particular instruction in your binary code. And we can do the same thing for both P and P prime. Therefore, we will get some a location map, node information mapping like this, like node 1 in the unoptimized code will be mapped to line 3 in your source code program. And location A in the optimized binary can also be mapped to line 3 in your source code program. Therefore, naturally, we should align this location A with 1, okay? And we can also get other source code locations, and therefore we can establish the node mapping. Next, we should also be able to build the edge mapping. Recall that in this control flow graph-like data structure, each node represents state transition, which corresponds to a basic block in your normal control flow graph. And in this particular example, the compiler chooses to emit a vectorized instruction that can do 8 things at a time. In order to generate this vector instruction, the compiler is supposed to know the semantics of this vector instruction and compare that to the original instruction and establish the fact that it is correct to replace 8 instructions with 1 single vector instructions. And we can also gather this information by instrumenting the corresponding code updating APIs in the loop vectorization path. Therefore, we can build the correspondence between, in this case, I think the non-trivial one is this one, right? So we can know that 8 scalar instructions, T2, corresponds to a single vectorized instruction in your optimized program. Okay. In other words, we can also establish the edge mapping. Once we have the node mapping and edge mapping, so we can basically we can build this alignment automaton, right? So once again, we can get the edge mapping and node mapping from the compiler instrumentation. Okay, so once we have this alignment automaton, we just add assertions to the different locations in your alignment automaton, and then use an S-engine solver to prove the equivalence. Okay, that process is the same as existing work, but the difference is that in this case we no longer need inputs, right? We no longer need to observe the execution of P and P prime in order to align these two control flow graphs. Okay, so I can also share some preliminary results, and we tried this approach on the benchmark programs provided in the existing literature, and we can successfully processing those benchmark programs and build alignment for those benchmark programs. And we also picked 2 recent bugs from LLVM's repository with respect to loop vectorizer, and we can also prove, using this approach, we can also prove the inequivalence of these 2 programs, right? Because that corresponds to a bug in LLVM. Okay. So to sum up, we kind of in this talk, I basically described the idea of doing compiler instrumentation and use the instrumented information to help with compiler testing and validation tasks. Specifically, I talked about 2 applications. The first application is related to debugging information, location information generation, and the second application is related to validating a loop vectorizer. And in both approaches, and we can see the same flavor, right? Instead of using additional inputs to test the P and P prime, we observe the internal behavior of your optimizing compiler, and then we use that auxiliary information to build the, to help the corresponding client applications. Okay, so I find this direction particularly interesting because it kind of bridges the gap between theory and practice. So in theory, we can develop a lot of sophisticated and nice static analysis frameworks, but in practice, in order to cope with the production compilers such as LLVM, it takes a lot of effort. And I'm trying to argue that compiler instrumentation information is the right sweet spot between the practical world and the theoretical world. All we need to do is, according to our specific application, and we instrument the corresponding APIs in LVM, and we can kind of use the instrumented information to help with the validation tasks. Okay, so in terms of future directions, I think there are a lot of exciting topics, both theoretical topic and practical topic. So in terms of the practical topics, I think it will be quite interesting to define the semantics of traces, right? So our goal is to build a principled framework on top of LLVM such that we can use those traces to express and analyze different kinds of optimization paths. And in this case, we have a lot of practical challenges to deal with. For example, in terms of the instrumentation, actually it's not very straightforward. You cannot naively instrument the instruction data structure in LLVM, because if you do that, you will see a lot of irrelevant log information. Therefore, we need to develop a certain filtering mechanism such that we will only be focusing on this instruction instrumentation with respect to your underlying application. On the theoretical side, we can view each compiler optimization path as a single program, and we could define the traceability of those optimization paths. In other words, is it possible to compute a minimum sequence of traces in order to tell that your optimization path is doing right or wrong on a specific input? Okay, so I think this is both directions are exciting, and I would be happy to talk to you offline. Okay, so I think maybe it's time to wrap up. And I think in the talk, and I tried to describe a general framework where we can use debug instrumentation to help with compiler testing and validation techniques. And the key takeaway is that we do not need input for your original program and optimized program. Instead, we can look at what compiler does to produce your optimized binary and to help with different validation tasks. And in the talk, I have gone through two applications. One is based on compiler debugger location information validation. The second application is based on validating a loop factorizer. And with that, it will conclude my talk, and I'll be happy to answer questions. Thank you.
Any questions? You can use the microphone.
Thank you for a nice talk. I'm wondering, the properties you make use of are very interesting, while they are still an under approximation of correctness. It's if these properties hold, it might be correct, but if they aren't, they doesn't hold, then it's incorrect. I'm wondering, do you think it's possible to finally approximate the correctness using a limited set of properties, or by using testing, or we still finally need to use some formal verification to verify the correctness of compiler passes?
Yeah. I think that's a good question. Especially that's the case for the first application where we want to validate the debug location property, and you can see that our oracle is actually based on a static analysis, right? So it's you can view it as over approximation. However, in the second application, we use an SNT solver to validate the equivalence of the two programs. In this case, I think it's more the precise equivalence property. So in other words, I think to answer your question, I think it depends on different applications. So sometimes for certain applications, it is beneficial to to do some static analysis and then use over approximation to develop an oracle. Because in this case, we are doing validation, right? We have to have an oracle, and we have to know where we are right, where we are wrong, right? In the first application, we use static analysis. In the second application, we use SNT solvers to prove the equivalence of two programs. I think yes, I think it's necessary, and it also depends on different client applications.
Yeah, and a follow-up question might be we finally found some real bugs in the state-of-the-art compilers. So do you have a intuition like is some compiler passes more easily prone to bugs, or have you analyzed the root cause of the bugs?
We have done an empirical study in 2016. I think the paper published at ISTA, and we did empirical studies and to analyze the different compiler optimization passes and how buggy they are according to the historical data. And I think according to that study, if my memory is right, the most buggy component in LVM at that time was the C++ front end in LVM. And in the optimizer, it should be like this insta combine, like this people optimizer. Yeah.
Thank you again for. Yeah.
Thank you for your talk. Very exciting, very interesting. Does your approach work with higher level languages like compilers of C++ or Java or Rust? And if I try to apply this technique for that kind of thing, what challenges, what difficulties would I face?
So I think this approach is language agnostic, and the key takeaway is that for whatever application you are interested in, you can always, right, if you want to do compiler validation and verification for whatever compiler you are interested in, instead of using like inputs to, maybe not this figure, but yeah, this figure, right? Instead of using inputs to validate the properties in unoptimized code and optimized code, you can instrument the internal behavior of compilers and then use that auxiliary information to facilitate this testing and validation process. That's the key takeaway, which I think is orthogonal to the choice of your language.
Hi, this was a very interesting talk. So you present the two different applications, and in the first application you basically look for the bug in the compiler. In the second application, you basically assume that the compiler is correct, and then use the information you obtained from compiler to do the validation for the transformation.
The compiler is incorrect. We cannot prove that compiler.
You're right. So you see this point, right? So
yeah.
In your future work, do you have any plan or idea to, resolve the conflicting issues?
Yeah, so that's a good point. So basically, that's a distinction between verification and validation, right? So verification focuses on the internal behavior of your software, and you can prove that your software is correct. On the other hand, validation provides no guarantees of the correctness, right? Even if it passes all your validation set, still you cannot prove that it's correct. But if you find issues, that shows that your implementation is incorrect. I think that's the difference between verification and validation, and we focus on validation. Yeah.
I'm wondering how fast is the analysis? Can I use that in a JIT compiler, for instance?
What
can I use that in a JIT compiler? How fast is the analysis? If I wanted to check if my JIT compiler it doesn't have bugs, for instance, and I want to check when I compile, like I want to apply this analysis. How fast is it?
So I think again, the key takeaway is to show the direction of doing instrumentation on your compilers and to help with your client application. In order to make this general idea work, you still need to analyze the properties. You need to have domain-specific observations of your underlying compiler optimization problems that you want to work with, and then instrument your compiler code accordingly in order to kind of see whether or not this information will be helpful for whatever application you are interested in. Did that answer your question? Okay, we can talk offline. Yeah.
So, more questions? Actually, we have 5 minutes.
I have one. So, in your approach, you remove the need for input for the programs you are checking? Do you think there's any path where you can also remove the need for the unoptimized program and explore the execution space of the optimization path?
Yeah, so that's a good question, right? So I think basically the beauty of get rid of the input is that in this case, we don't need to worry about the code coverage of your programs, right? Because in a traditional setting, in order to kind of validate the behavior, you need to be able to generate good inputs to kind of fully exercise the behavior of your P and P prong, and only then you can prove that, okay, the compiler is doing the right thing. And in our approach, we don't need such input where we utilize the internal knowledge of compilers. In this case, we don't need to worry about this like live code regions and dead code regions, and we can just like do the testing and validation.
The original program.
Yes, we need. Yeah, that's the point of validation, right? So validation, basically, you need to prepare a set of tests. Okay, so there are two, like, I think hopefully I can show the. Yes. So in a traditional setting, there are two levels of input. You have input to the test program, and you have test program to your compiler. And because we are doing validation, we have to obtain these test programs. But with our approach, we get rid of the need to kind of obtain the input to your test programs. Okay, it's still an interesting problem to generate those representative and good quality test programs to kind of exercise the behavior of your compilers. Yeah.
Thank you.
One more question. So I have one.
Okay.
So I'm curious, how effective is it compared to traditional approach? So is there any bugs that can be found by your approach, but not by the traditional technique?
The key takeaway is that we want to go beyond bug finding. So recall that in our first application, right, we not only can find bugs, but also we can propose patches. That is more valuable than finding bugs, because I think according to my previous experience, because LLVM is an open source project, right? If you only report a bug, the bug will stay there for several years or several months, and because everyone is busy. But on the other hand, at the same time, if you can propose a patch, and then it kind of dramatically saves developers time to look at this issue, and your patch can be accepted by the developers. Therefore, with the internal knowledge of compiler information, we can achieve the patch generation task as well, where in the traditional sense, we can only find the bugs. Like a live tool, you can only find the bugs, but you don't know how to fix the bug. But in our case, in the first application, once we find the bugs, we also know how to fix it.
Okay, thank you.
Thank you.
Okay, let's thank the speaker.